This is Module 7, Part 1, Lecture Part 1. So, we've already looked at the nervous system in a little bit of detail. Well, we're going to look at it in more detail this time. The neurons and the neuroglia. As I say, this is a fairly interesting module. Some of it doesn't excite me, but parts of it do. So the figure there on page 181 is a good general picture, figure, drawing. It's a good one to remember. It's a good one to draw because it describes, it portrays the defining difference in terms of your nervous system. Those being the central nervous system and then the peripheral nervous system. And we're going to discuss the both of them here in just a second, but they differ, and this little drawing is a good way to describe the both of them. So here we go. So the central nervous system, and it's important to become familiar with the acrostic for that, CNS. That's not a news organization, that's a central nervous system. But anyway, we'll use CNS a lot just because sometimes it's, it gets hard to keep saying central nervous system, central nervous system, central. Well, it's composed of the brain and the spinal cord, both encased in bone, the cranial vault, of course, of the skull, and the vertebral canal formed by the vertebra, and that's, of course, for protection. And so why would you want to protect that stuff? Because it's vital to you and to me. So the central nervous system. The peripheral nervous system, the PNS, consists of nerves and ganglia. So nerves are bundles of axons and their sheaths which extend from the central nervous system. There are two kinds of nerves. There are spinal nerves, and those are nerves which originate from the spinal cord, and there are 31 pairs of those. So in terms of the depiction there on page 181, that's what that's designed to show you there in terms of the spinal nerves. They are depicted all the way up and down there in terms of the spinal cord. And then the cranial nerves, those are nerves which originate from the brain, and there are 12 pairs of those. So you have a total of 43 pairs of nerves that make up the peripheral nervous system. And then there are ganglia, so that's the nerves. The ganglia are collections of neuron cell bodies which are outside of the central nervous system. So that is, again, some very basic descriptions of the anatomy, and we will flesh that out as we go. So the neurons of the peripheral nervous system, if you would, well, we're not quite there. This is still being discussed, that's right, on page 182. Important terms that, again, I guess the only way to get it is to continue to go over it and over it in terms of the Hebraic method of repetition. But the neurons of the peripheral nervous system, there are two divisions. There are the afferent division and the efferent division. So the afferent neurons are neurons which transmit action potentials, that's electric signals, from the sensory organs, your eyes, your skin, your ears, to the central nervous system. So they are the ones that say, this beverage is a cool, refreshing beverage. All right, AKA, of course, the sensory division. So if you're able to sense anything, if you're able to see it or hear it or touch it or smell it, That is because of the afferent nerves that are able to receive those stimuli and send them along to the central nervous system. The efferent neurons. That's better. So the efferent neurons are the neurons which transmit action potentials from the central nervous system, the CNS, to the effector organs, the muscles, the glands, also known as the motor division, and that has two sections itself, the SMNS and the ANS. So again, what we're talking about is the central nervous system transmitting signals to organs, muscles, and glands, these sorts of things, in order to do stuff. So you've received stimuli from your fingers saying this beverage is cool and it must be refreshingly cool. And so from your brain, it sends signals to your hand and the muscles in your arm to, it was refreshingly cool, to move that can to your mouth and so you can have a drink. And so afferent means to go to the central nervous system, and efferent means to come from the central nervous system. Now, remember, the efferent neurons also have two sections, the SMNS and the ANS. So the somatic nervous system, the SMNS, is the system that transmits action potentials from the central nervous system to the skeletal muscles. Those are the voluntary muscles. Those are the ones that just took the can of cool, refreshing beverage to my lips. All right? And then the autonomic nervous system, the ANS, is the system that transmits action potentials from the central nervous system to the smooth muscles. In other words, the cardiac muscles and glands. These are the involuntary muscles. And then that has two divisions, all right? These are the muscles that you cannot necessarily directly affect. Those two divisions of the autonomic nervous system, again, let's back up one more time. The somatic nervous system is the one that is sent from the central nervous system to your affecting hands and legs and lips and the rest. That's the somatic nervous system. The autonomic nervous system is sending signals to your liver and to your intestines and to your heart and these sorts of things. Well, the autonomic nervous system is also broken down into two, the sympathetic division and the parasympathetic division. The sympathetic division of the autonomic nervous system, the ANS, is that it generally prepares the body for physical activity. In other words, it increases the rate and strength of the heartbeat. It raises the blood pressure. It stimulates the liver to release more glucose to the blood for quick energy, for fight or flight. So the sympathetic division is getting you ready to take action in those muscles and organs that participate in that getting ready. It's not affecting the muscles that you will use to actually run away or fight, but it's affecting the anatomy that will do the physiology that will allow you to do that, to prepare you for that in terms of increased heart rate and production of various chemicals. The parasympathetic division of the autonomic nervous system is that which regulates resting and nutrition-related functions such as digestion and defecation and urination. So the parasympathetic division slows the heart rate for rest after you're done exercising. It lowers the blood pressure. It causes the smooth muscles in the stomach to churn for digestion and causes the salivary and lacrimal glands to secrete. So you've noticed it's probably not a great idea to have a big meal close to when you're going to physically exercise. You've played sports, or ran, or whatever you might do, you've recognized that. But on the other side of the coin, if you do, what happens is in terms of the sympathetic division, it's going to shut down very often what the parasympathetic division would activate. It's going to shut down the digestion and the churning of the stomach and the need to defecate or urinate. But on the other side of the coin, when the sympathetic division is not employed, then the parasympathetic division will kick in. And as a result, then these bodily functions, which obviously are normal, they will take place. So if you would, look at now, we finally reached page 183 and a new pretty little drawing, the nervous system at the cellular level. And again, the cellular stuff is okay. It's not my favorite part. But and incidentally, you should have 2 pages of notes, 4 pages total, front and back, but 2 pages of notes. And I'm at the bottom of page 1 in terms of your notes. So the nervous system at a cellular level, there are 2 basic types of cells which make up the nervous system: the neurons and the neuroglia. This course will concentrate on neurons, but you'll be surprised we're going to discuss the neuroglia some as well. So there is a neuron from the peripheral nervous system depicted for you, and this is not a bad job. Again, another something that, hint, you might want to draw. It might be good for your artistic endeavors. But the neuron consists of 3 basic units: a cell body and 2 types of processes: axons and dendrites, and we'll identify all that stuff in just a moment. So the cell body is called the soma, and it houses the cell nucleus, the mitochondria, which make the energy. It's the energy storehouse and production unit, the ATP, everything that the neuron needs. So the result of that is that they require a lot of oxygen. Neurons die in 4 minutes without oxygen. That is the issue, of course, for asphyxiation, for drowning, the various things. Neurons start to die at 4 minutes, and they do so in mass. So it's not just one and then another and another. It's many. So they require a lot of oxygen, and when they're deprived of it, that's a dangerous thing. The cell body has the Golgi apparatuses that secrete neurotransmitters that travel down the axon, where they are secreted from the synaptic vesicles. So if you notice some of that stuff that we just described, you see the depiction of some of the mitochondria, you see the depiction of the Golgi apparatuses as well, the nucleus, and it's not bad there. And of course then the designation of what the cell body is, going from them little hot dog things there, so to speak, to the arms with many fingers. So that is the cell body. So the dendrites are identified as well. Those are the little gray arms and finger things. The dendrites, they're shorter. They bring messages into the cell body. The signal travels down dendrites towards the cell body. So in terms of the communication of messages, that's how it's working. They come in from the dendrites. The axons are longer. They're microscopically short, or can be more than 1 meter long. So how about that for difference in terms of anatomy of these things? They send action potentials away from the cell body. So the axons are shipping out, and the dendrons are shipping in. All right. So in terms of the messages. And again, well, we're going to stay there, but turn over to page 2 of your notes, but stay on your picture there on page 183. Notice the axon hillock right as you come out of the cell body and onto the axon is the axon hillock. That's the area of the axon where, and again, it's portrayed, it's right in the middle, pointing to where it's at. On the bottom there of your drawing. It's the area of the axon where the action potential begins, and as we just sort of said, it marks the end of the cell body and the beginning of the axon. So that's the place of differentiation. Notice the myelin sheath. That's the hot dog bun around the hot dogs, okay? The myelin sheath is a fatty wrapping that speeds up transmission of the action potential down the axons. They're produced, as a matter of fact, by specialized cells. That's that neuroglia that we mentioned a moment ago, which have extensions that surround portions of that axon. In the peripheral nervous system, the neuroglia are called Schwann cells, all right? And neuroglia in the central nervous system are called oligodendrites. All right, so terminology is a little bit different, but in terms of what they do, they're very similar. Notice the nodes of Ranvier. Those are gaps in that myelin sheath. So you see the nodes of Ranvier as depicted there. The collateral axons are splittings of the axons, and again we'll look at more of what all that stuff is about in just a little bit. But notice the collateral axon. That's the series of hot dogs that come off the main trunk of hot dogs. All right. And then the presynaptic terminals or terminal boutons. They are endings. There they are, the presynaptic terminals. They are endings, where was I? There we go. Endings of the axons into branches. Axons cannot undergo mitosis. The human body is estimated to have 100 billion neurons. Under normal conditions, human beings lose 7,000 neurons a day, which amounts to about 0.03% of neurons. And I might add, though, and this is an important caveat, that alcohol and drugs destroy neurons. So prolonged alcohol use, prolonged use of certain drugs. The current rage, state after state, is legalizing marijuana and cannabis for personal use. It's another thing in terms of the development of some of the components in cannabis that are used medicinally, and I think probably to great success. I have a son-in-law who suddenly at 33 began to experience grand mal seizures of epilepsy, and he's tried various drugs, regular chemical drugs, to control those seizures with some success, but also with side effects, and some of them are not so good. But he's actually had pretty good success from use of some of the byproducts of cannabis in terms of controlling those seizures. I've heard of it was almost miraculous for a little baby boy who was having hundreds of seizures a day, if you can imagine that, epileptic seizures. And as an experiment in Alabama, this was a couple of years ago, they put him on, again, a cannabis-related medication, and he's down to like 3 or 4 a day, which that's still a lot, but it's a whole lot better than hundreds. So that said, there are medical opportunities in terms of that drug, but recreational use of marijuana just in and of itself the cannabine in marijuana kills brain cells. It just does. And when I was a kid, there was these movies and it depicted stoners as, you know, hey man, hey, what you doing? And, you know, that sort of thing. That's a physical reality. That's changes in the brain by virtue of the death of brain cells that leave people less ambitious, more willing to sit around and do nothing, less inclined to be able to learn. So, you know, I'm not your mother. I can't tell you never to try marijuana, but I'm here to tell you, it is not the safe, fun drug that it is depicted to be in so many places. If you go to secular university, you're going to find it everywhere, and you'll probably be peer pressured to try it. And I'm just telling you straight up, for so many reasons. Spiritual, psychological, and then physical. Stay away from that stuff. I'm done. So, all right, so neurons are classified based on their number of processes in terms of the extensions. So now we can turn over to page 185, and there is there's another depiction of these things. So there are unipolar neurons, there are bipolar neurons, and then multipolar neurons. So take a look at the one on the left. That's an afferent neuron. It's a unipolar neuron. It means one process, and the cell body sort of hangs off that process. You see there in terms of the cell body to the left of that thing. And the dendrite is a pseudodendrite because it sends signals toward the cell body, but in a manner of an axon. Afferent neurons, they're usually unipolar. So that's kind of an interesting thing. These dendrites, as I say, they have a action potential that goes in the direction, but not necessarily to it. Then there is the bipolar. Let's see, what is our signal here? Oh, that's north. Okay. Let's get rid of this. I don't know why that's done that. There it goes. Yeah, Jacob, I lost you last week, and I'm sorry. I've tried to remind myself to make sure this thing is still going. I have no idea why. Well, actually, I do have an idea why. We lost connection. I think my battery died. So, trying to remember to check in on you. You doing okay? All right. All right. So bipolar. That's. I won't make the joke. That has two processes, and you see it in terms of the middle depiction there, the two processes. There's an axon and a single dendrite split into lots of branches. The example of bipolar neurons are specialized afferent neurons, such as the eyes to the brain. So in terms of sending signals to the brain, remember this, to the central nervous system. And then finally there are multipolar neurons, and they possess many processes. There's several dendrites, but only one axon. No matter how many processes a neuron has, it will have only one axon. And as you see, that's depicted to be the case in each one of these illustrations there, from unipolar, bipolar to multipolar. These are often motor neurons. They are part of the efferent division of the peripheral nervous system, sending signals to the effector cells, such as muscle cells, or they can be association neurons, a neuron that conducts action potentials from one neuron to another within the central nervous system. So in terms of multipolar neurons, they can work for both the peripheral and the central nervous system. So we can get to the neural glue, and I can still get your stuff, and we can go from there. Again, remember I mentioned to you on the onset the chapter is more about the nerves, but we are going to discuss the neuroglia as well. Turn over to page 187, and there are depictions of several different types of neuroglia. We've already looked at a couple of pages back. You saw the hot dog type here in terms of the Schwann cell. Well, let's look at them in detail. So the neuroglia is the neural glue, or the connective tissue, so to speak. It's not actually connective tissue, but it's, so to speak, of the nervous system, and is a majority of the nervous system. A little more than half of the brain's mass is neuroglia. How about that? There are 9 neuroglia to every 1 neuron. Neuroglia are much smaller, and as you see here, they are depicted and exist in 5 types. So they are oligodendrites, Schwann cells, microglia, astrocytes, and then ependymal cells, and there's 2 forms of those which they're depicted and we'll discuss. So the oligodendrites, look at the top of figure 7.1, and that's what an oligodendrite looks like. They are found in the central nervous system, and they bind the neurons together. They insulate the axons, and they wrap around several axons. So see how it's depicted there in terms of axons, and look at the oligodendrite as it is also depicted. So you've got several different axons, and there is the oligodendrite insulating them. The Schwann cell is what we saw a moment ago, the hot dog sort of thing, the hot dog bun, really encapsulating the peripheral nervous system neuron. Schwann cells are found in the peripheral nervous system. They insulate neurons. They wrap around only a portion of one axon. We noticed that again a couple of pages ago, based on that wrapping only a portion does not include the node of Ranvier. Remember, that's that section back on 183 that is sort of in between the hot dog buns. All right. The microglia. They, look at that thing there in terms of the microglia. They engage in phagocytosis to fight infections. White blood cells of the brain and spinal cord. There's not many brain or spinal cord infections. Perhaps you've noticed. There's just not. And part of the reason for that is the effectiveness of the microglia. The astrocytes they form the blood-brain barrier. That is the barrier between the capillaries and the brain. And this is absolutely crucial. It is necessary because many substances that other parts of the body need are toxic to neurons. Nutrients and oxygen are brought into the neurons by the work of astrocytes and specialized cells in the capillaries in terms of what comes in from the blood and what is sent out of the tissue into the blood. Not all substances that are toxic to brain cells are held back. The high brought on by most illegal drugs and also kills brain cells, affecting memory and learning, well, those things pass through the blood-brain barrier. That's the reason for the high. It's affecting your brain. It's killing your brain, all right? In terms of alcoholism, sadly and tragically, if you've known someone who has been an alcoholic for a number of years, if you get older, you will know someone who was not an alcoholic and then many years, and and you'll see the changes in them. And part of those changes has to do with the ability to remember and the ability to learn. It passes across that blood-brain barrier. So there are two types of strokes. I think we've discussed this before, but one of them is the form that happens as a result of a vessel in the brain that becomes clogged, and so blood supply does not get to the brain. Those are dangerous, of course, those types of strokes, but very often they can be helped and the effects reversed because not as many brain cells die, and at least in a short period of time, as a result of those clogs, and clot-busting medications can be administered, and so the clot is opened or the clog is opened, and normal brain function can be restored. The other type of stroke is the result of a blow to the brain or bleeding on the brain. Somehow a vessel opens, and so what we just mentioned in terms of the toxic nature of certain chemicals, well, blood, especially the iron, the heme in blood, is death to brain cells. And so in terms of concussion, the concussion protocols in sports have gotten so much more strict, I think that's the right way to say it, than since I was a kid. Same thing in all of the sports, but professional football in especially. I mean, the guys, they'd get knocked out and they'd go sit down for a while and they were right back in. And sadly, horribly, tragically, so many of those men died young as a result of repeated concussion. Concussion is another word to say bleeding on the brain, therefore death of blood cells. Not too long ago, I can't think of the name of the actress, but if you watched a 90s movie, what was it, the one about the twins? What's that thing called? I can't remember. Lindsay Lohan as a kid, when she was a sweet kid. I can't think of the name of that movie. What was it called? Say what? I still can't hear you. Yes, thank you very much. Thank you very much. See, it's the blood-brain barrier that's been affected in me too. I can't remember. So the actress who played the mom in that movie, she was the wife of another actor, Liam Neeson. I'm sure you've probably seen his stuff. But she was skiing and fell, hit her head, and was fine. And it was later that night, or maybe the next day. I don't remember the exact sequences of events, but she either blacked out or fell or something. But she died, and she died as a result of that blow on her brain and the slow leakage of blood into her brain. So this is for your sake in terms of the course and learning the course, but it's also the opportunity for me to remind you of the importance of taking care of yourself if you hit yourself. And you know, I run into doors and walls all the time, and that's not what I'm talking about. But if you get hit, if you fall, if you hit your head in a way that you're dizzy or you're just not right, and you know that, a good chance you need to get checked. Let's finish the last two and we're actually done. Again, we've been able to actually get through the 2 pages. So the unciliated and then the ciliated ependymal cells, that's the last 2 depicted here. The unciliated secretes cerebrospinal fluid that bathes the brain and spinal cord and provides a protective cushion around the central nervous system. That's what the unciliated ependymal cells do. And then the ciliated ependymal cells move cerebrospinal fluid around so that it stays homogeneous. In other words, keeps it in the proper way. So you recognize the importance of the proper maintenance, the homeostasis of cerebrospinal fluid around your body when you spin yourself. round and round and round and round. And you come out of that spinning going, you know, right like this. And the reason is your cerebrospinal fluid in terms of the movement has not caught up and become homogeneous again, and so you are dizzy. So we're going to stop there, and we'll look at nerve structure the next time, maybe the least favorite part of this module. But is there any questions on this stuff? Kind of interesting stuff, I think. I'm still awake. Let's see, some of you are, all right.